In question number 7, we're going to attempt to revisit what we learned in Unit 4 about inverses, and this might be a great time, if you haven't yet, to see if you still have any materials from Unit 4, namely the page in the Unit 4 packet where we introduced the concept of an inverse. We did lots of practice with switching x and y, or doing a little table method to find an inverse, and many people ended up formulating a preference about which inverse method they liked to use. If you forgot, then I'm going to try, if I can, to make an executive decision to have everybody use the same method, no matter which one you preferred way back in Unit 4, because that will help those of us who have forgotten, since it's been so long, and it'll help those of us who aren't really sure, like, well, how do I know which method is going to be best? As a reminder, we learned 2 ways of finding inverses in Unit 4. We talked about that little table method where you write out the steps and then you just reverse the steps in the opposite order. And we talked about switching the letter x and the letter y and just solving each problem algebraically. Again, I'm going to make the executive decision here, and we're going to do all of the problems in these videos with the switching x and y to solve algebraically. If that's not the method that you remember preferring, you are welcome to try to figure out how to do these the other way. It's actually not hard, but this is the way that most math analysis teachers do it, with the switch x and y. And since the whole purpose of this chapter is to better prepare you for math analysis, I feel it's my responsibility to do the problems the way they will, so that way it's all familiar. Now, you don't have to answer question numbers, letter A, parts 1 and 2, because ordinarily this would be a class discussion. We would talk about both methods. We would compare them. We would see which one takes more time or less time. We would really debate the relative merits of each one. And since we're missing that opportunity to have that dynamic conversation, we can skip that question in favor of all just kind of using the same method for the sake of efficiency. We're going to switch x and y to find an inverse. In case you're like, wait, what does that mean? I'll do this one as an example so you can remind yourself about exactly what it means to find an inverse. First step in finding an inverse, literally switch the letter x and the letter y in the original problem. So if the original problem was y equals, we'll write x equals. The numbers in the operations don't switch, it's just the literal placement of the letters x and y. So the 3 stays where it is, the plus stays where it is, the log base 4 stays where it is, and the x becomes a letter y. So notice it's the exact same looking expression as the original problem. I just switched the letter x for the letter y, and vice versa. Now, our goal is to get y by itself. So it's really kind of a 2-step process, and I'll write the steps over here if you're a note-taking person. Step 1 was to take the original problem and switch x and y. Step 2 will be to get y by itself. And hopefully this is where your algebra instincts do kick in a bit, because getting y by itself is something we've spent all year kind of working our way up to. Getting y by itself often means moving anything on the same side of the equation to the opposite side. And usually we work from what we call the outside in. We start with things that are furthest from y and we get rid of those first. And then we get ourselves closer to the letter y and get rid of those things later. So as I'm looking at this expression, I can see that the 3 is really easy to get rid of because it's pretty far away from the y. And it's linked with a plus sign. We know that to get rid of the 3 to the other side, we'll just do the opposite, which would be subtract 3 to both sides. So that means I'll have x minus 3 equals, now the 3's are canceled out, log base 4 of y. Now I want to refocus on my goal. I want to get y by itself. And I'm looking at y saying to myself, wait, how do I get y by itself? That means I have to get rid of the log. And hopefully, after the last few videos, you've gotten the idea that to get rid of a log, you'll need to write it in exponential form. That's really why we do this. We get rid of logs by writing things exponentially. Just how we get rid of exponentials by writing things as logs. That's why they exist, so you can use that opposite idea. So I'm going to take this expression and rewrite it as an exponential. Now, if you're not comfortable with rewriting it exponentially this way, because you're like, wait, this doesn't look like the ones I already did. I'm used to the log being on the left-hand side. You can just rewrite the problem really quickly so that the log appears on the left. and the x minus 3 appears on the right. We haven't changed anything. And it's fine to do it visually that way because some people like doing that and use the little pattern a bit more easily. So they remember that arrow pattern and they can say to themselves, okay, yeah, I see the order now. We know that to write this exponentially, we always start with the subscript, the base, so the base will be 4, to the power of whatever's on the opposite side of the problem. And this time, this is the first opportunity we've had to do something that has a little bit more going on, but that means the power is going to be x minus 3. It's okay to have more than one thing. At whatever is on the opposite side of the problem is the exponent. So if it's x minus 3, then so be it. Even if it's not a single number, that's okay. Then we have equals whatever's attached to the log in its base in the first place. So equals y. And then I look at what I wrote and realize, oh hey, y's by itself. That's what I wanted. So you can see why we do it. No pun intended. It's to get the letter y by itself. We get rid of logs by writing it exponentially, and notice it effectively canceled out the log and got y by itself. So this expression, y equals 4 to the power of x minus 3, must be my inverse. Now, it's not really worth belaboring the point too much, but it is actually worth taking a second to realize that if you had to, specifically if you had the technology to do so, you could definitely check to make sure that everything that you just wrote is actually a true inverse. One of the ways that you can do that, if you wanted to, was to look at the graph and to make sure that the graph that you see is truly the graph of a proper inverse. Now, I can show that to you quickly on a graphing calculator, and if you want to use Desmos for this, you definitely can. Eventually, we'll talk about, if you have a graphing calculator, how you can type these things yourself. For now, I'll just type it very quickly. Log base 4 of x, oops, I forgot the 3, was the original equation. And we just found that the inverse was 4 to the power of x minus 3. And if I graph those two things together, what I'm expecting to see is that same line of symmetry, that same effect where if I rotate it kind of diagonally, I can see that they're symmetrical straight down the middle with y equals x as that line of symmetry. So we can visually confirm these two are definitely good inverses. We can tell that they're perfect. Of course, you don't have to do that for every single problem, but it is worth noting that's another option besides just like checking the answer key. In the last video, we'll do a couple more examples of inverses, but if you feel like you can do this, feel free to skip the last video and use the answer key on your own.